Okay, well, I'll carry on. So we'll we had formulated a variational problem for geodesics on a surface, and the way I've set it up is I started off with R3 and a parameterized surface like that of a sphere in R3, and the Pythagoras theorem in R3 led us to this concept of the Riemannian metric on the surface. And where I want to go today is give you an example of a surface where all, once the geodesics are found, all the Euclid's axioms, but fourth, but fifth, are satisfied. But the example I'm going to give you will be what's called an abstract surface. So we're still going to use the concept of the surface in a Riemannian metric, but we're not going to be assuming that this surface is embedded in R3, and that's how modern theory of surfaces evolved. So abstract surface. Abstract here stands for that I'm not thinking of the surface as coming from some embedding in R3. In fact, the example I'm going to give you, it can be shown, it cannot be globally, locally it can, but it cannot be globally embedded in R3. So for us, an abstract surface would be a pair consisting of the surface and the Riemannian metric. And this Riemannian metric is still of the form E dx squared plus 2f dx dy plus g dy squared. And it's still the case that the length of the curve on this surface is given by an integral of square root of this between some 2 points on the surface. Now, I'm going to give you now a concrete model for this surface, okay? And it's called the upper half plane. So perhaps those of you who are mathematicians would have studied this upper half plane in the context of complex analysis. I'm not going to use complex numbers. So I'm saying that x and y belong to R2, but y is greater than 0. So the x-axis doesn't belong to the surface. The x-axis is the boundary of the surface. Okay? But the novelty for us will be that I'm going to use a different notion of the distance, so a different Riemannian metric on this surface, not the Euclidean one, but something else. And this Riemannian metric is this: dx squared plus dy squared over y squared. that's what we will be substituting in this length functional, looking at the Euler-Lagrange equations. So E equals G equals 1 over y squared, and F equals 0. Okay. And our objective now is to figure out what 2 points on this surface P2, what's the shortest path, shortest with respect to this Riemannian metric connecting? I mean, if I were to use the Euclidean metric, then the shortest path would be a straight line, but it will turn out that it's not a straight line with respect to the metric we use. So we need to find. Okay, and I want to make I didn't take my notes with this, obviously, of doing things in real time, and in order to simplify the calculations as much as I can, I'm going to use this approach again I mentioned yesterday. Rather than parameterizing my curve by t, so I rather than saying that my curve gamma can be parameterized by x of t and y of t, I'm not going to do that. I'm going to parameterize this curve by x. So rather than saying that t goes to x of t, y of t, I'll have x and y of x. So that will give me, instead of having Euler-Lagrange equations with 2 dependent variables, I have one Euler-Lagrange equation with 1 dependent variable. Okay. So now these points P1 and P2, they have 2 values of x corresponding to them. This one has x1 and this one has x2, and they joined by some curve, and the length of this curve is an integral from x1 to x2 of square root of this. So I'll have a square root of dx squared plus dy squared over y, but I'm thinking of y as a function of x. So that's the same as an integral from x1 to x2, square root of 1 plus y prime squared over y dx. So you see, the one slight disadvantage of this parameterization, parameterize the curve by x, is that for that to make sense, I need to assume that x1 is different than x2. I need to deal separately with the case where x1 and x2, if my P2 was on the same x value as P1, then what I'm doing wouldn't have worked. But this is a special case, and I'm going to deal with that one at the end. Right? So I'm assuming that x1 is not. Fine. So this is now our functional f. Well, this is now our Lagrangian f in which I'm going to put in the Euler Lagrange equations. And I try this equation, but remember, whenever we can, we exploiting this concept of first integral, and there are two types of first integrals I've introduced. One arises if little f doesn't explicitly depend on y, and another one arises if it doesn't depend on x. So in our case, it doesn't depend on x because no x. So, is there anyone here who actually took notes? Like, I want to look at the number of certain equations I had yesterday. It'll be towards the beginning of my first lecture yesterday.
2.4, yeah.
The energy. Exactly. Use 2.5. So if I do, f only depends on y prime. I can use 2.5 between 4, and that gives me f minus y prime vf by vy prime equals constant, or this constant c. And here I compute. So I have a root of 1 plus y prime squared. So now I'm kind of relying on you, or at least some of you, to correct me if I make a mistake in my calculation. I think I know what I want to get, but I'm not sure how I get it. Okay, so but I'll do my best. But if you look for mistakes and you see what I'm telling. This divided by y minus y prime. Now I have the derivative, so this is y prime 1 minus y plus y prime squared. C.
With the y, right? There's a y in the
denominator. So now I bring this into a common denominator. So I multiply up and down by a root of 1 plus y prime squared. You see, so in the denominator, I have y root of 1 plus y prime squared. And in the denominator, in the numerator, I'll take the square of this, because 1 plus y prime squared minus y prime squared. So it's 1. And that's equal to c. Okay, so now I'm separating the variables, squaring. So my value is like 1 over y squared c squared by the look of it, minus 1 equals y prime squared. And this I could write as 1 minus y squared c squared over y squared c squared. Right. So now, now I need to take square root and separate variables. So divide by by dx equals square root of this, square root of 1 minus c squared y squared divided by cy. So now I separate and integrate both sides, and I get c integral y dy divided by root 1 minus c squared y squared equals an integral dx, which is x minus x0. X0 is a constant integration. Now, starting now. And to say that we need to be integrated by substitution. So if I say that, let's say that cy, let's say that c squared y squared, I want to be double. So 2c squared y dy is clearly dw. So I have this y dy looking at me here, and I have this c looking at me here. So I need to put 2 here, bring this c here. I need to bring another c. So I square this, I divide by c, and I think possibly in good shape, because now I have 1 over c integral of dw divided by a root of 1 minus w equals x minus x.
Should you have a 2 in the denominator?
A 2 in the denominator because I've manufactured 2. Yeah. Okay, it's kind of hard to. This is the thing of COVID. See, COVID. I didn't lecture on the blackboard for 2 years, and I kind of run out of shape. I would sit with my notes and look at the notes. I mean, before COVID, I would always look on the board without notes. One gets rusty. Right, but this I can integrate. So this integrates to, and the integral of this is twice 1 minus w, possibly with the minus sign. Is that correct? Because if I differentiate this, that appears to be correct. Appears to be correct. So this 2 cancels, and I get minus. Worry about this minus, but let's see. Maybe it's not. I think it's harmless. 1 minus w over c equals x minus x0. Go back here. Now let's forget about w. W is good. So I have, but I'm tempted at this stage to square both sides. Let me square both sides. So I get 1 minus w over c squared equals x minus x0 squared. 1 minus w is 1 minus c squared y squared over c squared. Maybe it's not too bad. It's not too bad. It's not good. x minus x0 squared. Okay, so I find, so this C divides out, and I end up with x minus x0 squared plus y squared equals capital R squared, where my R squared is just another name for 1 over C squared. R, which is 1 over C, and x0 are constants of integration. Okay, so we've solved the problem, see, and the solution is B. These are circles. Well, they're not circles because the whole circles don't belong to our universe. Our universe is only the upper half plane. So these are semicircles, and these semicircles are centered on the x-axis. So now let's go back to our picture. Y is supposed to be greater than 0. Two points, P1 and P2, and I can always, so it means that for any, so these 2 points have 2 values of x, and these values of x are constants of integration, and from these constants of integration, I find the other 2 constants I need, that is r and x0. So I find the center of the semicircle and the radius of the semicircle, and I can do it in math because 2 equals 2. So that the semicircle is centered on the x-axis, and it contains these 2 points. So it's centered on the axis, it intersects it at my degrees. That appears to be my x0. Some radius. So there exists a unique semicircle through any 2 points. Well, with our assumption that these points have different x values. Okay, so we have, we know almost all geodesics now, where are these semicircles. But we still have to figure out the case, but that's an easy one. What happens if the points have the same x value? So since we think of, well, we are 2 ways, and we can do it directly, which I will, or by limits. So, what take P2 and get with P2 closer to the x value of P1. Well, what happens is our semicircle still centered at the x-axis, but starts having huge radius. And in the limiting case, for x1 equals x2, the radius of the semicircle becomes infinite. It becomes a line, a horizontal, a vertical line. But we can also see it directly. By going to our functional. So if x1 equals x2, that is this situation, and if I compute good, I know. Then, if x1 equals x2, then I can parameterize. Rather than parameterizing my curve by x, I can parameterize it by y. Now, I have these points have different y values, y1 and y2. I have y1, y2. I have 1 plus, well, I have bx squared plus y squared over y. That's x prime. Now prime stands for b and b. Y plus 1 over y dy. See, now I can just bound it from below. So this is definitely greater or equal to an integral of dy over y with an equality if and only if x prime equals 0. Right? Clear. So for distant minimizer, we want this to be smaller, so we want this lower bound to be saturated. So we need x prime equals 0. That means that on our geodesic joining P1 and P2, x doesn't change. But that means that it's just a line segment. So the geodesics are sum up. Geodesics are circles or line segments. By the way, this I should have said at the beginning. This upper half plane, the notation for it is H. Not to be confused by its quaternions or anything. H for hyperbolic plane. Are semi-circles centered on the x-axis or vertical lines. Given by x equals constant. So now let's see why this breaks Euclid's space axis, keeping the other four intact. Again, h, y greater than 0. So this x-axis doesn't really belong to a hyperbolical plane. Now, remember Euclid's fifth axiom. for any line L and a point P not on L, there exists unique line containing P not intersecting L. That's true in that is true in Euclidean geometry of the plane, because it's our configuration point line, and there is a unique pair. Okay, now what happens here? Well, pick this line L. We can pick it as we want. For example, the line L can be this: semicircle centered the x-axis. And pick a point P. Well, maybe make it low. Now, I claim that there are infinitely many lines, which are physics, which go through P and don't intersect L. So first of all, we have this one, the vertical line, but we also have all these circles which the only thing I want from the circles is that they cross the x-axis at 90 degrees, so they centered at the x-axis. And all these lines contain P by geodesics, but they don't intersect L. So this is not true on H, as there exists infinitely many lines of geodesics parallel to L. So, so that's a model of a non-Euclidean geometry. And that, I mean, perhaps I should finish this bit off with giving or mentioning that there is an equivalent model, but without doing the calculations. So, have you done? Do you know what the Mobius transformation is? Maybe you know them. Maybe you know them under different name.
The complex one, right?
The fractional linear, sometimes they call them.
Yes, I'm familiar with it.
So now let's bring complex numbers to this for a moment. So I'm defining another definition of H is that this is Z in the complex plane, and such that the imaginary part of Z is greater than 0. Same thing. I just have to say that Z equals X plus I1. And I would have done everything in terms of complex numbers, but it's actually easier in this model to work with X. Now, recall, I say, Mobius transformations. So you tell me if you're seeing, so Z, what are they? Z goes to M of Z, it's defined to be A Z plus B divided by C Z plus D, under the condition that A D minus BC is not equal to 0. Have you seen those? So how do you call them? You haven't seen those. And is it that the physicists having seen those and the mathematicians have, or is it vice versa?
Vice versa. Yeah.
Well, okay, so what I'm going to say now might not make that much, well, you'll have to take things on faith, okay? These are lovely transformations. And one, so what, okay, so let's do this kind of interact. I mean, I'm myself, you see, I'm against interactive teaching. I mean, it's nonsense. You teach professor comes, they kind of, in 50 minutes you listen and you kind of take notes. And that's how things have been done. But the modernizers say, no, teaching should be interactive. You should kind of talk to each other. And maybe things like anthropology or history, maybe that works. Normally it works in mathematics. Anyway, let's try that. So what the guys who've seen these Mobius transformations, what do you remember? What are your favorite facts about Mobius transformations? Yeah?
They are compositions of geometric transformations such as translation, rotations, dilations, I believe.
Yeah, there's one that you can decompose them into single ones.
And they are biholomorphic, I believe, away from the singularity.
But if they biholomorphic, because you have a problem, okay? If your things go wrong, if Z equals minus D over C. So what we really do, you need to attach a point to a complex plane, a point at infinity, and that's called the extended complex plane, and then they are biholomorphic on this extended complex plane. That's not what I need from my kind of thing here, but that is true. What else do you know about Mobius transformation?
I don't remember much.
Okay, one thing which really follows from this definition is that there exists a unique Mobius transformation mapping any free points on this expanded complex plane to any other free points. Okay, so let's say that I give you Z1, Z2, Z3, and I want them to go to W1, W2, W3. Then you can work out exactly what these constants have to be. The constants are not uniquely defined because you can divide by one of them. So there are really three constants in that, and these three constants are fixed by free points. Okay, so if you want to have some region on the complex plane and you want to see where this region goes, it's enough to take any 3 points on this region and see where they go, and that'll determine your Mobius transformation. And another consequence of this definition, because they biholomorphic in particular, they are continuous. And so if you have a bounded region, and the boundary of that region is mapped to the boundary of the new region. Okay, so where I want to go with it this is following. If I take this picture, this upper half plane, so let's say that Z belongs to the upper half plane. And I consider the following Mobius transformation. So M of Z equals Z minus I divided by Z plus I. So that's a special case of this, where A and C are both equal to 1, B equals minus I, and B equals I. Well, so in terms of X and Y, this is X plus I, Y minus 1, divided by X plus I, Y plus 1. Okay, that's what we call the sum. Now, remember that Y is greater than 0 on the upper half. So one thing that follows from this definition is that if I take mod W squared, which is W times W bar, well, that is X squared plus Y minus 1 squared divided by X squared plus Y plus 1 squared, then this is definitely greater than 1. No, better, smaller than 1, which is where I want, smaller than 1. It'll be equal to 1 if Y equals 0. Because if Y equals 0, then I have minus 1 squared is 1 and 1 squared is 1. Now, if you think about it, not too hard, I think I've told you. You'll see that what this Mobius transformation does is it maps this upper half plane onto a disk, onto an interior of a circle centered at the origin. Say W equals 1 if Y equals 0. So we have upper half plane and this upper half plane is bounded by the x-axis. So x-axis is not really part of upper half plane. And there is this Modus transformation. Z goes to Z minus I divided by Z plus I. And that maps this upper half plane to the interior of a unit disk. Disk consists of complex numbers W such that mod W smaller than 1. And why that's relevant, I'll tell you after the break. Okay, so let's break for a few minutes. know everything there is to be known about the upper half plane. We've figured out all the geodesics. They either circles centered on the boundary or they straight lines. And it doesn't satisfy Newton's axiom. And there is this Mobius transformation from the upper half plane to the interior of the unit disk. Now, the Mobius transformations, I recommend them to you. They are good things to study in whatever part of maths you're interested in. There is an interesting group theoretic aspects because the Mobius transformations form a group under composition, and this group has many interesting discrete subgroups. And they, but one thing which I'll use say is that Mobius transformations map circles and lines to circles and lines on the complex plane. So a circle will go to a circle or a line, a straight line, and a straight line will go to a circle, a straight line. So you can ask, well, you know from this, once you figure that out, you'll know what will happen to geodesics. So there are two types of geodesics. There are the straight lines, and there are the semicircles. And they'll be mapped to either semicircles intersecting this boundary by 90 degrees or to diameters. So this disk model, it also has geometry on it. You can take this Mobius transformation and you can see what happens with this Riemannian metric. We started with, which was dx squared plus dy squared over y squared, which in terms of z's is dz bar divided by z minus z bar. So this z minus z bar. Z minus z bar is 2y. So if I square that, I have minus 4y squared. But I don't need minus 4. So I need to do this. That's this Riemannian metric on the upper half plane in terms of z and z bar. And you can compute what happens to it in terms of w, and you'll find that this is dw bar divided by 1 plus mod w squared. No, it's rubbish. Not plus, minus mod w squared all squared. So we could have started with this Riemannian metric on the Poincare disk, on this disk, and find the geodesics, and we would find that they are the circles and lines, but the way we've done it, it follows from this Mobius transformation. I'm telling you this because although it's easier, it was easier for me to do calculations with this model of non-Euclidean geometry, the upper half plane. This is the model you see more often in books and also in art, Escher's art, where this non-Euclidean hyperbolic geometry is depicted by this disk. Okay? But for my purpose, our purpose, let's stick to that. So that's it. We've done with non-Euclidean geometry and geodesics from variational perspective. So we'll still have some time to talk. And I think, okay, so I can tell you several things. But I can tell you, I think I propose to tell you one of two things, and you tell me which one you want, and I'll tell you. I can either go back to the beginning when we did the first variation and we derived Euler-Lagrange equations as necessary conditions for an extremum, but we don't know whether it is a minimum or a maximum, and to determine that we need to look at higher order terms in the variations, and that will take us to second variation. Or I could tell you, not about second variation, but give you another example of where Euler-Lagrange equations appear in geometry, and tell you about what's called minimal surfaces. So this surfaces of soap films, minimizing the area between two wires. Which one do you want?
The second. First.
Should we vote? Vote. Democracy. I hate democracy. But let's- Fine. Who wants second variation?
No, the second variation, which is the first.
Oh,
right?
The second variation, the first topic.
I don't know.
Not necessarily, because there can be people who abstain. One, who wants the minimal surface? Minimal surface with democracy.
There's more people.
But then, this will come again with my plea for help, because I prepared that. My plan was to do the second variation, so I prepared that. The minimal surfaces I'll be doing from in real time. I think I know where I'll go, but there'll be a calculation to do, but we'll get.
Can you send us like some notes? Of
I sent Hiba notes, and Hiba will distribute.
Okay, cool. Then we can help you.
So so there'll be section 4. Minimal surfaces. It's a big subject, and this minimal surface is still subject of current research. And it's a nice one because it brings pure mathematicians, applied mathematicians, and theoretical physicists together. You're interested in this, and pure mathematicians because there is some lovely geometry analysis still behind it. Applied mathematicians because these minimal surfaces really appear as energy minimizers for soap bubbles, which real serious people look at soap bubbles, how they look like. And theoretical physicists because some of the minimal surfaces give you ground states of vacuum states in string field. But we'll just do the basics. Okay, so maybe this. Consider two closed wires in R3. By wire, I mean curves. So here's one, here's another one. And what we'd like to do is to construct a surface which has these wires as a boundary, and such that the area of this surface is minimal. Call them gamma 1, gamma 2. What is there? No, first of all, there is existence. Does such a surface exist? And sometimes it doesn't. Maybe it looks something like that. You don't want it to be too thick because the area grows. You don't want it to be too thin, but the thickness can change from point to point because of the shape of these wires. Maybe if the wires are too far apart or one is far bigger than the other, maybe there is no such surface. And then another thing, there is uniqueness. So if there is such surface, is it unique or can it have more? Very difficult problem. So we will look at the simplest but already non-trivial case of first examples of such surface. We will assume that both wires are circles, and we will assume that our surface is rotationally symmetric. So it's what one calls a surface of revolution. I'll tell you exactly what I mean. That's my z-axis. That's my x, y. And I take one wire to be a circle, and this corresponds to z equals L, circle, and another wire to be also a circle, at z equals minus. And the circles have the same radius. And this circle also has radius. Okay. So I have these two circles. So what sort of surface can connect this? Can you think of a surface which connects these two circles and has them as a boundary? A cylinder. But cylinder, you know, it might not be best. In fact, it is not best. So for cylinder, we can compute the area of a cylinder, but you can imagine that making the cylinder thinner in the center, near here, might decrease this area. The cone. Well, the cone is not best either, but cone is not really a surface because it's singular at the origin. But you see how thin do you want to make the cylinder? Well, if you make it thin, that creates more area here. It's not clear. It's really not clear what the solution is. I mean, it seems like there should be a solution, but what is it? So that's what we're going to do. We're going to find the surface. It was done. Euler was the first one done. Okay. But we're going. So the surface will without telling too much, the surface will look a bit like that. And I'm going to assume in my derivation, in fact, it can be proved. Well, I'm going to assume in my derivation that this surface is rotationally symmetric. So it's a surface of revolution, which really means following. If I take this curve and I rotate this curve with respect to the origin, that's why it's my surface. So a cylinder is an example of such a surface because I just rotate a straight line, right? So let's start. So I need to compute the area element of this surface. So let me start with what coordinates shall we use? Is it because of this rotational symmetry? I think it's best to use cylindrical coordinates. I'm going to use Z, and instead of X and Y, I'm going to use R and, how do you call cylindrical coordinates? R and theta, you call, yeah? Now, what's the area? Why do that? So if I pick, I do it the kind of high school way. So let me pick some section of this circular section, and make it a bit thicker. And I want to compute this area element, and then I want to integrate that to get the whole area. So I need, what do I need? I need the circumference of the circle for some given r times the length of this here. The length of this I claim from Pythagoras' theorem in cylindrical polars is dz squared plus dr squared. So it's important for me that you're happy. I don't force you to be happy, but try to understand why this is dz squared plus dr squared. You see, z goes up and r measures, and r goes that way. R measures this distance. So this is really Pythagoras' theorem that this block is dz squared plus dr squared. So the infinitesimal area element called dA is circumference, which is 2 pi r times the square root of dz squared plus dr squared. Now, good. So now comes a choice for us. And if I worked this out last night, I would have known by now which choice is best. I mean, we can do with both choices, but I'm going to just force one of them. To find the surface, it's sufficient to find this curve, right? Because if I know what the curve is, I can just rotate it. So on this curve, I can either think of z as a function of r, or I can think of r as a function of z. I can think of z as a function of r, or I can think of r as a function of z. Which is best? I don't know. But I'm going to think of, I'm leaning towards thinking of z as a function of r. Z as a function of r. So on the curve and the surface, z is z of r. So our surface parameterized by r and theta. So now what's the area function now of the surface? Well, we need to integrate, of course, also integrate between integrate 2 pi. Actually, no, because I don't have the theta because I already put 2 pi. So I've done the theta integral. So I just have one integral. I have 2 pi integral r square root of 1 plus z prime squared. Yeah. Maybe I made the right choice. So this is now f. And this f So R plays the roles of X, independent variable, Z plays the role of Y. So F depends in general on R, Z, and Z prime, but our F doesn't have explicit Z dependence in it. So I would need to write, because I'm using different letters, not to lose you, let me write the full Euler-Lagrange equations. Euler-Lagrange, because I want to find the dependence, R dependence of Z, which makes this the area minimizer. So I have df by dz minus d by dr df by dz prime equals 0. You see, but df by dz is 0, so df by dz prime is a constant. df by dz prime equals c equals constant, the first integral. And that should give us an ODE for z, which we aim to solve. So what's df by dz prime? And there's this r here looking at me. Fine. So it appears to be z prime times r divided by 1 plus z prime squared square root, and that equals c. And that's an ODE, first order ODE for z as function of r. Okay, so r squared z prime squared equals c squared plus c squared z prime squared. Okay, so z prime squared equals c squared divided by r squared minus c squared. So dz equals c divided by square root r squared minus c squared dx. Yeah. dr. So I'll integrate. See, let me do, okay, fine. So z minus z0 equals an integral. Now let me divide up and down by c. If I do that, I'll have down by c. Down by c. So I have 1, or I have 1 I have R over C squared minus 1 dr. Okay.
Trigonometric substitution.
Hyperbolic, I suggest. You see, let me do this. I have this R over C. So change this to R over C. The omega to multiply by C. And now, am I looking good? Or am I looking? I think I'm looking good. So I propose the following substitution. R over C, I want to call cos, we've done hyperbolic functions, cos W. Okay. So D of R over C is sin W dw. Now I get Z minus Z0 over C. So I'm dividing by this C here, equals an integral of sin W dw divided by square root of cos square W minus 1. Cos square W minus 1 happens to be sin square W. So I take a square root, take a positive square root, and this sin W cancels. So this is just W. So this is W. And I don't need to worry about constant of integration because it's already there in Z0. But W I've defined to be, okay, so W is
Cos inverse.
yeah, cos inverse of this. Okay, so the best way for me to proceed now is to take, I have this equation and I take cos of both sides. So I say cos of Z minus Z0 over C is cos W, but cos W is R over C. So I think I've solved it. So my question is R equals C times cos of Z minus Z0 over C. That's the solution. Tells me how it, so that tells me how R depends on Z. And this curve is called the category. I mean, you know, it was the simplest minimal surface. So the curve is category. What's the terminology? The curve is called category, but sometimes people refer to the corresponding minimal surface also as the category or catenary. And it's a surface of revolution of this catenary. So let's push it a bit more, see what this constant corresponds to. So remember on the z-axis, I have L and I have minus L. And I have these circles. And circles are called given, which means that they have some radius, given radius. Let's say this radius is capital R. So these are the two wires people gave me of radius R, and these wires are twice L apart. It's a bit like this. So what? So first thing I want is I want that R of L must be equal to R of minus L, and that must be equal to R. Okay. Well, the only way this can happen, if I put Z equals L, or I put Z equals minus L, I want to get the same thing, I must have Z0 equal to 0. Because cosh is an even function. And so now with Z0 equal to 0, I can see what happens where Z equals 0. So R takes its minimal value. If Z equals 0, then cosh of 0 is 0, but I have this C looking at me here. So I have the interpretation of C. C is the radius of a circle of the minimal radius, which cuts the, Z equals 0 flag. Okay, so now I have this canoid in full. Let me therefore write my final solution as R equals R0 cosh Z divided by R0. Okay. But now there's a formula. But now if you really think about this problem, might say, does this, some formula, does this surface really exist? And what can go wrong? Well, I think what can go wrong is following. If this L is very big, then, and if R is also big, I mean, the maths will give us that. So what you might worry about is that, if R is fixed, let's say that R is fixed, and you play with L. If you make L too big, this catenary becomes thinner and thinner, and if you try to stretch it more, it will just break. Okay, it will not exist, and that, we can experiment with. Experiment with that. If you ever played with this soap bubble, so you take two plastic rings, and they connected by a soap bubble. Okay, and this soap bubble really looks a bit like. And then you gently pull these plastic rings apart. Well, the bubble becomes thinner and thinner, but of course you're not going to pull it to the moon, right? Because it will break. So we don't always, on the kind of intuition grounds, we don't always expect this to exist. But let's see if we can find the condition. It will be something to do with if I can do it right, and I really don't remember. I don't remember how it's done, but we can figure it out right together. Or I will. It'll have to do with the ratio of capital R to this R. And it shouldn't be too hard, because all I need to do is look at the boundary. Okay, good. Then I know where to take this. So let's take this, which is really our key equation, and now let's substitute the boundary condition. And the boundary condition now is that if I put z equals L, then little r has to be capital R. So r equals R0 cos L over R0. Let's divide both sides of this by L, capital L. So now I have R over L equals R0 over L cos L over R0. See, R0 is not given. R0 follows from, R0 follows just by substituting z equals 0. So our data is only L and capital R. Now, this is the equation I want to analyze. I want to see if this equation has solution. So let me call this equation star. Does star have solutions? Okay. To see that, let me call L over R0. I want to give it a name. Call it A. So how does my equation look like? If L over R0 is A, then I have R over L times A. So I'm now multiplying both sides by L over R0. So this would be multiple of this would be 1, and L over R0 becomes here. Equals cos A. Well, when I solve this equation for A, it's not an algebraic equation. There is no quadratic formula for it because there is hyperbolic function. It's non-algebraic equation. So I mean, it's hopeless to think of a formula. Huh? But if it is, then we use graphical. So how can this equation possibly have a solution? Well, it can have a solution if these two graphs intersect. So we're drawing a graph, so that's A. And we're going to draw two graphs. One of them is a graph of cos A. Well, we know how that looks like. Cos of 0 is 1. And then cos looks like this. Okay. And what is this? Well, that's a straight line, and the slope of this line is given by R over L. And it either intersects this or not. So here's a straight line, and that corresponds to small R over L. Here's another straight line, and that corresponds to large R over L. Okay, so that agrees with our experimental bubble intuition, because what we're saying is that if capital R is fixed, so the radius of this wire is fixed, if you try to, pull them too far apart, so if L is large, then the slope of this line will be small, and this line will not intersect the graph of cos, so there are no solutions. On the other hand, if L is small, then there are two solutions. and two solutions. So there are, we don't have uniqueness. So we might not have uniqueness for small l. There is a critical value. That one you can find numerically what that has to be, the ratio of R over L, so that there is only one solution. So our conclusion is for large R over L, there exists two minimal surfaces. And that that's very strange. That if you try to create a soap bubble, nature would create one for you because nature minimizes these variational problems. But it can do it in two ways, and they're not close to each other. So one will be thick and one will be thin. So people who've studied those in the 20th century, I mean, it's non-trivial to say what happens. But if you push it, and for that we really need the second variation and some engineering. And you can look it up online, and there are some elementary presentations of it. But elementary, but they can go beyond the first course of variational methods or even minimal surfaces. You find that only one of these bubbles is stable. So, and quite honestly, I just don't remember whether it's whether it's this one which is stable or that. One of them is stable, and the other one, if you perturb it slightly, it breaks. But the stable one, if you perturb it, it bounces around and it settles. But that's not an issue for this critical value of R over L, because there you only have one surface. But below this value, you have none. So, we've solved this catenary problem with existence but possibly non-uniqueness, and that's why I propose to stop. And I'm going to send some notes to Hiba, and she can then distribute them amongst. So I wish you guys all the best in your education. I might come back in September, so I'll see you again.
Thank you. Thank you very much.